Alright, so I think I'm recording. We're taking a look at rational functions, and for these problems, we're interested in the end behavior of the graph of these rational functions. We begin by recognizing these rational functions are a ratio of polynomial functions, and we want to compare the degree of the numerator against the degree of the denominator. Whenever you compare two values, if you are comparing two numbers a and b, there's only three possibilities. Either a is less than b, or b is less than a, or a is equal to b. So when we compare the degree of the numerator against the degree of the denominator, it always falls into one of three categories. So here I see my biggest exponent. These are all terms. My biggest exponent on the variable is 5. The degree of my numerator is 5. I look down here and I see that I have two like terms here, that this would be 8x to the fourth. Well, I can see that the degree of that is 4. Okay, so here I refer to this generally as top heavy, and when it's top heavy, there is no horizontal asymptote. Okay, that's the one case when we don't have a horizontal asymptote. So to describe what's happening far away from the origin, we need to plug in very small values into this ratio, very small values of x as x is approaching negative infinity, and then also plug in very large values of x is approaching positive infinity. So if x is approaching negative infinity, I know that y is either going to be positive or negative infinity. I have to determine what the sign will be. As x is approaching positive infinity, what is y doing? So all I have to do is to use the leading terms. As x is getting really, really small in a negative sense, in the numerator here, this x to the 3 and this xx are not contributing to the magnitude of the number. This x to the 5th dominates those other numbers. It's like these other terms are just grain on the sand of a beach. A single grain of sand doesn't even amount to the entire beach. Well, that's kind of the idea, that as x is going to negative infinity, this middle term here dominates the other terms so much that it's insignificant. All right, and the same in the denominator here. These lower degree terms, the x to the 4th and x cubed, don't really have anything to do with the magnitude of this ratio as x is going to negative infinity. So as we plug in values that are negative, and I'm just going to use a negative sign to represent some really small number, negative a million, or you could put negative infinity in there, I guess. I just don't want people to think that I'm doing arithmetic with negative infinity. I'm just abstracting the idea of a really small number. So if I have a negative 4, and I don't even care about the size that it's for, just that it's negative, and I'm multiplying that by some negative number that's being raised to the 5th power, then a negative base raised to an odd power is going to be negative, but a negative times a negative, this numerator is always going to be a positive value. And in the denominator, I have 5 times, well, what's important is that it's positive. This negative number is being raised to an even power, so that's going to be positive, and a positive divided by a positive will always result in a positive real number. So I know that as x is going to negative infinity, y is going to positive infinity. All right, so now let's plug in extremely large values, large in the positive sense, and in the numerator we have a negative number times some positive number raised to the 5th power. Well, a negative number times a positive number is going to be negative. And in the denominator, I have 5 times some positive value raised to the 4th power. Well, a positive times a positive is because if this base is being raised, well, since it's positive to any exponent, it's going to be positive. But when we have a negative numerator divided by a positive denominator, the final answer is going to be negative. So we know that as x is approaching positive infinity, that as you're going to the right, you also must be going down in this graph. So here's our end behavior for this graph. Now, we can confirm this answer by looking at using Desmos. I've already keyed it in. So I don't know what's going on close to the middle of this graph, around the origin. But I know that when x is going to negative infinity, as you move to the left, y is going up. So I know the end behavior is going up on this end. I changed the color. That this is going up to positive infinity. And I know that as x is getting bigger in a positive sense, the y's are getting smaller. So I don't know what's happening in the middle of this graph. I would have to look and see, are there vertical asymptotes, are there holes? I would have to find x-intercepts and y-intercepts and all of that business. That, we could do that, but what we're doing right now is just simply determining the end behavior. We believe it's going to look like this, so let's go check it out on the graph and see if it is. All right, so what do we got? Let's turn off the graph from number 1, turn on the graph from number 2. So if we zoom out, we can see that close to the origin, you have a vertical asymptote here, but far away from the origin, it's behaving exactly like we thought it would. Let's take a snapshot and send it to our page. And that's kind of nice. It pasted it underneath what we wrote. We said it was going up to the left. Well, that's true. It's going up to the left over here. And to the right, we said it was going down as you move to the right. That's exactly what we predicted. We didn't make any predictions about near the origin. We just said the end behavior was no horizontal asymptote. Horizontal asymptotes become horizontal. They become a flat line. This end behavior, as you move away from the origin, it's not becoming a flat line. So I hope that helps.